We once crowned this the largest star ever found. But that crown is already slipping. Drop the giant where our sun is, and its surface would reach out past the orbit of Saturn. And yet, we are no longer sure it is really that big at all. That doubt is not a small footnote. It is quietly unmaking one of the most famous claims in modern astronomy. But how do you measure a giant you can barely see? And what do you do when the measurement turns out to be wrong? You are watching Orbix. Over the next few minutes, you will meet a monster of a star, watch its crown slip, and by the end, that uncertainty will feel less like a failure and more like a gift. Let us start with the size, because the size is almost impossible to hold in your head. Picture our sun. Already more than 100 Earths could line up across its face. Now picture a star so wide that light, which crosses from the sun to Earth in about 8 minutes, would need hours just to travel from one edge of it to the other. That is the scale we are talking about. By one estimate, made in 2012, this star, Stephenson 218, stretched close to 2,000 times wider than the sun. Set it in the sun's place, and you, the Earth, Mars, Jupiter, all of it, would be inside the star. You would not orbit it. You would be buried somewhere deep within it. To give that a shape, imagine lining up 2,000 suns edge to edge. That whole line is the width of a single star, a width your mind can never quite stretch around. Its outer layers are so thin, so faint, so puffed out, that it is less a solid ball and more a glowing ocean of gas, one you could drift through for a very long time before you ever found the core. Sit with that for a moment. Every ocean you have swum in, every city, every person you love, tucked somewhere inside one star. And that star is only one flicker in a galaxy of hundreds of billions. From out here, your entire world is a warm speck, and somehow that thought is easier to sit with than to fear. Where did this giant come from? In 1990, an astronomer named Charles Bruce Stephenson was scanning a dusty, hidden corner of our galaxy toward the constellation Scuti and found a tight cluster of aging red stars. One of them, catalogued later simply as number 18, seemed to tower over all the rest. These are red supergiants, stars near the end of their lives. They have burned through the fuel in their cores, swollen outward, and cooled to a deep ember red. Stephenson 218 looked like the most swollen of them all. And here, in that faint red glow, is where the trouble quietly begins. Turning a glow like that into a real size takes a chain of guesses. You measure how bright it appears, you assume how far away it sits, and the math hands you a radius. Do that with the old distance, and the answer came back a monster, the largest star in the universe. The headline raced across the internet, through documentaries, into classrooms. But a star that big, at that brightness, breaks a rule. Physicists talk about a ceiling called the Humphreys-Davidson limit, a point where a star pours out so much light that its own radiation should rip its outer layers away. At 2,000 suns wide, this star sat far above that ceiling. By our own physics, it was almost too bright to be real. Now, when nature seems to break a rule, usually nature is fine and our numbers are not. So astronomers went back, carefully, to the one thing everything else was balanced upon, not the star itself, the distance to it. Get that number wrong, and every other number bends with it. Here is something strange about this star. We have never actually seen its surface. It sits nearly 20,000 light years away, buried behind clouds of dust that smear and redden its light. Point our sharpest telescopes at it, and you still do not get a clean disk. You get a blur. How do you even size up something you cannot see clearly? You work backwards. You gather all the light the star gives off and add it into a single number, its total power. Then you lean on a simple truth. A hotter surface glows more fiercely, a cooler one more gently. Knowing its temperature and its total power, you can solve for how big it must be. But every step of that hinges on one guess. How far away is it? Assume it is farther, and to look this bright, it has to be enormous. Assume it is closer, and it can be far smaller and still shine exactly the same. The size was never truly seen. It was inferred, and it rode entirely on the distance. Could the whole crown be resting on a single, mistaken guess? There was really only one way to find out. Stop inferring the distance and measure it directly, even for a faint star half swallowed by dust. And think about what that uncertainty really means. The biggest star we believed we had was, in a sense, a shadow cast by an assumption. From far enough away, even our confidence starts to look small and a little fragile. There is something oddly calming in that, in a universe patient enough to keep correcting us. So what if the distance was simply wrong? For most of astronomy's history, we had no clean way to check. The old estimates for this cluster ranged wildly, from nearly 100,000 light years down to under 20,000. That is not a small correction. That gap, on its own, is the difference between a true monster and something merely enormous. To settle it, you would have to pin down the distance to a dim, dust-wrapped star with almost impossible precision. For a long time, that was hopeless. And then a small spacecraft changed the game. This one was built to do a single thing, beautifully. Measure distances. Its name is Gaia. It watched stars shift by tiny amounts as our planet swung around the sun, a wobble called parallax. It is the same trick your eyes use when you hold up a finger and blink one eye, then the other. The closer the finger, the more it seems to jump. Turn that method towards Stephenson 218, and the dust makes it brutally hard. But as the measurement sharpened, a picture began to form, and it did not match the legend the star had been handed. The star looked closer than we had assumed, possibly much closer, maybe a foreground star, sitting in front of the cluster rather than deep inside it. And if it is closer, it does not need to be a giant to look this bright. The revised size falls from around 2,000 suns to something nearer 1,000, still staggering, but no longer the largest. So who wears the crown now? The honest answer is that it keeps moving. A star called WHG 64, out in a neighboring galaxy where we can pin the distance down cleanly, sits near 1,500 suns across and is one of the safest contenders we have. Others rise and fall with every new reading. Scuti, once celebrated as a champion, was quietly cut down to size by better data. The title of largest star is not a fixed fact. It is a leaderboard, and it reshuffles every single time our instruments get a little more honest. And here is the detail I keep coming back to. Even in its smaller, corrected form, Stephenson 218 is close to 1,000 times wider than our Sun. Remember that number. It would still swallow the inner planets whole. Light would still take more than an hour to crawl across it. We did not lose a giant. We only learned to describe it honestly. Because whether it is 1,000 suns wide or 2,000, this star is doing something our Sun never will. It is dying out loud, bloated, unstable, and shedding its own body into the dark, one shell of gas at a time. One day, on a timescale far longer than any human story, its core will collapse, and it will tear itself apart as a supernova. In that final flash, it will seed the dark with the very atoms that go on to build planets and oceans and you. Even the largest stars are temporary. That may be the most reassuring thing about them. It is easy to hear all this and feel small. But smallness does not have to mean fear. The same uncertainty that shrank this star, remember, is also the reason the cosmos keeps surprising us. A universe that can still overturn its own biggest claims. Well, that is a universe with plenty left to find. So look up tonight toward Scuti, where a dying giant hangs behind its veil of dust. You cannot see it clearly, neither can we. We measured it wrong. And honestly, that is the best part. Because from that distance, every worry you are carrying right now fits inside a single, quiet point of light. We are small. Our certainty is small. And somehow, that is a relief. If you want to keep drifting outward with us, the next journey is already waiting on the channel. The biggest black hole we have ever weighed, the sound hidden inside the dark, the strangest objects we have ever found. Follow along, and let's keep measuring this universe gently and together.